Hello, and welcome to Lecture 4 of Gauss's Law in Phys 1204. We've got an informal statement of Gauss's Law, and we've already been able to use it to do quite a bit. Now we're going to get a formal statement of Gauss's Law, which is very powerful for calculating electric fields in certain situations. The reason our statement of Gauss's law so far is informal is that our definition of electric flux is very informal. We've defined it so far as simply the number of lines passing through a surface. And note that that makes it arbitrary, because the number of lines we draw into or out of a charge is arbitrary. However, it has some properties that we do need. It's proportional to the electric field strength, because the density of lines is proportional to the electric field strength, and it's proportional to the surface area of the surface that the lines are going through. This informal flux definition is technically not the electric flux. It's technically something that's called the field line flux. But it basically only differs from the electric flux in that it's in arbitrary units instead of in useful units connected to charges and field strengths and so on. So now we're going to construct a formal flux definition, and to start with, it's going to be incomplete. The easiest thing to do to get something that we need, which is proportional to the electric field strength and proportional to the surface area, is just to define the flux through a surface as simply the electric field strength times the area of the surface. But that's missing a couple of things that we know it needs. For one thing, we know that if we take the same surface and tip it relative to the E field, so it's no longer perpendicular, then the flux decreases. And so clearly just multiplying the electric field strength by the surface area isn't quite good enough. There has to be some angle dependence. Second of all, in our definition, whenever we are working with a closed surface, when the field lines go out of the closed surface, they make a positive contribution to the flux through the surface, and everywhere they enter the surface, they make a negative contribution. And so our formal flux definition is somehow going to have to include this sign convention. However, we can already state what the units of flux must be. If we're working in SI units, then this E field is in newtons per coulomb, and this area will be in meters squared, and so the units of flux must be Newton meters squared per coulomb. So let's develop our formal flux definition further. So far, if we ignore sign, then it's good enough as long as the E field is perpendicular to the surface, so that there's no angle dependence that we have to worry about. Well, to figure out the angle dependence, I'm going to think about the flux through a rather odd shape. Here is the shape. It's sort of a trapezoidal prism. So there's a back surface and a front surface. There's a constant E field in this region, and it's passing into the back surface and out of the front surface. And note in particular that the back surface is perpendicular to the field. If you find this three-dimensional picture confusing, look at the two-dimensional picture, and hopefully it'll help you make sense of it. So there's some area of the back surface and some area of the front surface. The reason I've chosen this odd shape is that calculating the flux through the back surface is straightforward. It is simply the electric field times the area, except that since the electric field is entering, it has to be negative. So the flux through this back surface has to be just the negative of the electric field strength times the area of the back surface, since that surface is perpendicular to the field. Now we're going to use this surface and work out what the flux through the front must be, and use that to get the angle dependence. Well, to use this shape to figure out the angle dependence of flux, we're going to have to make a key argument. And you're going to understand this argument if you figure it out better than if I explain it to you. So it's time for you to figure it out. So here is the surface in both views that I've showed you, and note that the lines come in the back surface, and so as I've already pointed out, the flux through the back surface is by definition negative. And I'm just going to make up a number. Let's suppose the flux through the back surface is negative 100 Newton meters squared per Coulomb. What's the total flux through this surface? As usual, if you're doing this through Moodle, then Moodle will require you to get this question right before it allows you to move on.